Hello, everyone. I'm Georgina Rayner, and I am the Associate Conservation Scientist at the Strauss Center for Conservation and Technical Studies at the Harvard Art Museums. And today, I'm going to talk to you about our study into the binders and pigments used in the traditional Aboriginal bark paintings. Before we begin, I would like to acknowledge that the land on which I live and work is situated on the traditional and ancestral territory of the Massachusetts people. I also respectfully advise that this presentation includes the works and names of deceased people. We'll start today with a brief introduction, or maybe reintroduction for some of you, to the Bark Paintings project, and then we'll move on to the results, looking at the analysis of the pigments and binders separately. I'll end the talk today with some of the conclusions we were able to draw from this project. Back in 2016, the Harvard Art Museums hosted Everywhen, the eternal present in Indigenous art from Australia, curated by Stephen Gilchrist. Alongside the development of the exhibition, the Strauss Center undertook the first large-scale technical investigation into the pigments and binders used in traditional bark paintings. This project has been going for many years, starting back in 2012. More recently, working from home as a result of the pandemic really provided me with the time this project needed to study and reevaluate the data, drawing final conclusions and to write it up as a publication. The project set out to answer two main questions. Firstly, can we use the elemental fingerprint of a paint sample to trace its source? Research has previously been done to provenance Australian ochres and demonstrated that an ochre's elemental composition varies across the continent. With our study, we're aiming to look at if the same is true when looking at samples taken from paintings. The second question addresses whether binders were commonly used, and if so, what were they? This question originated from the widely held idea that bark paintings developed out of the tradition of creating short-term shelters in wet weather. And based on this idea, it was commonly thought that Indigenous artists would not have used binders. Working with art galleries and museums in Australia, we sampled 48 paintings and 3 objects, including 2 shown here from the National Gallery of Victoria collection. Where possible, we took a sample from each of the 4 colours of the traditional palette: white, red, yellow, and black. The samples were taken in duplicate, with 1 sample for pigment analysis and 1 sample for binder analysis. Working with artist centres, we gathered samples of natural ochre and binders used by artists for comparison with the samples taken from the paintings. Shown here is the natural yellow ochre deposit on Bathurst Island in the Tiwi Islands that we included in our study. Working with artist centres also offered us the invaluable opportunity to learn about artistic technique. Malcolm Wepanda kindly demonstrated for us how an orchid may be used to prime the bark before painting. In the images, you can see Malcolm rubbing the bulb of the orchid, which has been freshly picked, directly onto the bark surface. And Nyapa Nyapa Yunupingu demonstrated how the paint is prepared, grinding the ochre rock with water on a breeze block before mixing with a binder. This map summarizes where our reference materials and paintings originated. Our focus has been on artworks originating in the Northern Territory, in particular Arnhem Land, and the surrounding islands, with a small set of paintings taken from the Kimberley and Western Australia for comparison. Overall, we had 180 pigment samples and 191 samples for binder analysis. For some paintings, we also were able to take a small sample of the bark substrate so we could look for any preparatory materials, which is why there are more binder samples. We collected 25 natural ochre references, 8 different potential binders, and a sample of bark. So let's move on to analysis, and we're going to start today with the pigments. To look at the elemental composition of our reference materials and samples from paintings, we used laser ablation inductively coupled plasma mass spectrometry. The technique has previously been used for studying ochre provenance, and the results provide an elemental profile of all the major and minor elements used in an ochre. To make sense of the elemental data, it was necessary to understand the mineral composition of the paint samples and ochres. And for that, we used both FTIR and Raman spectroscopies. So what minerals were present? For the majority of white samples and ochres, we identified the presence of kaolin, which, being an aluminosilicate, has high levels of aluminium in the ICP-MS data. We also identified huntite, a magnesium calcium carbonate, and we found the occasional occurrence of mica, calcite, magnesite, and barite. We also found a lot of quartz around in general, and we see all of these white or colorless minerals in our red, yellow, and black materials as well. I'm grouping the red and yellow together because they were both iron oxides, so both very high in iron content. We can differentiate between them with Raman, with the red ochres identified as hematite and the yellow as goethite. The majority of our black samples and ochres were manganese rich, which indicated a manganese black pigment based on manganese dioxide. We tried to identify the minerals using Raman, but manganese blacks are notoriously difficult so we didn't get much further with that. Samples that had very little elemental content we found to be carbon-based, typically a charred plant material. And then for the longest time, we had an unidentified black in our samples. It was manganese rich, but also had a considerable zinc contribution, which meant that it did not fit with the other natural manganese blacks. There is mention of the use of a black pigment from dry cell batteries in the literature, and when we tested one, we found it was consistent with what we were seeing. So we call this third black battery black. It is the only synthetic pigment we identified, and we'll talk a little more about where we found it later on. Let's get to thinking about the idea of using the elemental composition to trace the source of an ochre. We're going to focus on the trace elements. That is, elements present but in smaller amounts, as these are more likely to vary, and maybe that variation can be related to an ochre source. And we're going to use ternary diagrams like the one shown here, which are commonly used for looking at rock and mineral composition. Using this plot, we can look at the relationship between three elements. So, for example, here we have rubidium, strontium, and barium. I've now added here all the data from our white samples and reference ochres. It does look complicated, but we can break it down. We have clear groupings. So we have Yirrkala samples and ochres circled in red, and the Tiwi Islands circled in green. Looking at the data, we could maybe even suggest that the Yirrkala group could be split into two groups, or maybe even three groups. And maybe that suggests three different sources of ochre. Now, that said, we have to be careful because we're only working with a small sample set. And if we were to add more data to this, we might find that these groupings become less clear. And maybe really it's just one larger, more dispersed group. This group are samples we identified as being kaolin mixed with barite. Here's a sample that contained mica. And then this group is our huntite containing samples. So with this ternary plot, we were able to differentiate between pure kaolin, kaolin with additives, and non-kaolin whites. And we can see that pure kaolin whites from different locations can also be separated. This was very, very exciting for me because it shows that it does seem possible to trace a white ochre to a location based on its elemental profile. However, this data set shows us that we face a challenge that will center around what materials the artist chooses to use for a painting. In our study, we looked at 3 different paintings from Owen Pelly, and each one of those used a different white. So that's 3 different sources of white ochre for one location. This highlights the need for a better understanding of where artists traditionally source their ochres and the choices they were making for their pigment. This is as far as we could get with the data for our white materials, and it is encouraging. So next up, we have red and yellow. In this ternary plot, we're using lithium, thorium, and uranium as our elements to compare. And here I've put in both the reference materials and the samples onto the plot. We have a group that includes material from the southern areas of the Northern Territory, although it does include a couple of additions from within Arnhem Land. Our lone sample from the Tiwi Islands groups with the Tiwi Island ochre references, which is shown in blue. And then we have 2 other groupings shown here. The Yirrkala samples, which are grouped in red, and the Groote Eylandt samples grouped in green. The samples from these two places are very dispersed, and I delved into secondary materials, other minerals that might be present, but I couldn't find any correlation. So at the moment, there's no clear reason why these samples are so dispersed, which is why I've not tried to make any smaller groupings within these locations. It is interesting that we have this area of overlap between these two larger groups, and it does make me wonder if they are related in some way. Perhaps this could be an indication of ochre trade between communities, but again, more research is needed. So while some grouping is possible, the red and yellow ochres present a more complicated picture than we saw for the white ochres. And we're going to look at the black ochres next. And whilst working through the data, I found that ternary plots like this were not going to work for those materials. I could not find 3 elements that would represent the 3 different types of black pigments we identified. So instead, I played around with the data and found that using a logarithmic scale for the manganese and zinc data was the key. The logarithmic scale is a way of displaying the numerical data that occurs over a very wide range of values in a compact way. And when we plot our data, we see 3 clusters of data points: our manganese black samples, our carbon black samples, and our battery black samples. So interestingly, the battery black samples were primarily found on paintings which originated in Groote Eylandt. These paintings date to the 1940s, so after foreign settlers are known to have arrived on the island, bringing their batteries with them. There are manganese deposits on Groote Eylandt, and we did find its use on one painting, as well as on another painting, we found the use of carbon black. So this analysis suggests that artists on this island would use all of the black pigments, so whether natural or man-made, available to them, and it indicates a very adaptive use of materials. This alternative approach to looking at data means that we were not able to necessarily trace the geological source of black pigments, but we can readily identify different sources of black pigment, and there have been geographical connections that can be made. The second half of our study was focused on the use of binders. We've heard mention of orchid, beeswax, bloodwood, egg, and even blood, to name a few in our research, but there was no definitive identifications about what materials and when they might have been used. Some of our reference material for binder analysis is shown here, and for the analysis, we use both FTIR and pyrolysis gas chromatography mass spectrometry. FTIR is a great first step for looking to see if there is a binder present in the sample. Gums, resins, and proteinaceous materials have unique spectra that we can identify. However, it's a little more complicated when the pigment gets involved. Today, we're going to focus on the pyrolysis GCMS work because we found it to be the most effective for identification. Shown here are the chromatograms of our plant-based reference materials. Some materials gave a very strong signal, like bark and bloodwood, whilst others, like orchid juice, Kalumburu, and Wattle, have a very weak response. So we have to look closer to the baseline. The chromatograms from pyrolysis GCMS of these reference materials are complex. So the next step was to identify marker compounds for each material. And I've marked here the areas of interest for each one. The gray bars are from the derivatizing agent used during analysis, so we can ignore their peaks because they're unrelated to the sample. And ultimately, we ended up with a table of marker compounds for each material. The table is not exhaustive, but the compounds represent both pyrolysis products with the highest abundance, as well as products with a lower abundance identified to be unique markers. This is an example from a sample. Again, we can ignore the gray peaks as they're unrelated. The blue bands represent marker compounds for bark, and those peaks are quite strong, having a good abundance. The pink bands are for orchid juice, and those peaks are a little harder to see. So if we focus into where the orchid juice markers are between 18 and 35 minutes, you can see that those peaks can be very tiny, but they are identifiable by searching with the ions from the table. So let's talk about orchid juice some more. we identified, or can at least suggest its presence in 42 out of the 51 artworks included in the study. And the works were from both the Northern Territory and Western Australia. And significantly, we were able to identify it as both a preparatory layer on bark, as we saw Malcolm demonstrate earlier, and as a paint binder. And we found it on the earliest known bark paintings, which date to the late 19th century. So painted before any art market existed for bark paintings, meaning that we can suggest that binder was used historically. The second binder we identified was bloodwood. Its use has anecdotally been described as a Western Australian tradition. We identified it in 5 paintings, the 3 included in the study that originated from Western Australia, but also in 2 paintings from the Northern Territory. So whilst it might be true that it is a Western Australian tradition, the use of bloodwood is not exclusively a Western Australian tradition. We did not identify any of our other reference materials, plant materials or non-plant materials such as egg during our analysis. The only other resins we commonly saw were synthetic. And here are some UV details of some samples. The resins are readily identifiable on the surface, so we can consider them to have been applied as consolidants. We found 7 occurrences of the use of cellulose nitrate. And from our research, we know that Charles Mountford described spraying paintings with it during the 1948 expedition to Arnhem. The coated paintings all date to 1946 to 48 and are from Yirrkala and Groote Eylandt. So maybe this finding connects them to this expedition. We also identified butyl methacrylate. The majority of these paintings did not have any record of consolidation, but based on what we know about the use of butyl methacrylate as a varnish, we could suggest it was used sometime between the 1930s to the 1970s. The last resin we identified was polyvinyl acetate. It is used by Aboriginal artists nowadays as a binder, and we did find it used as such in some of the more recent paintings included in the study. But we also saw it used as a consolidant for older paintings, which predate the introduction of artist centres, which is when the use of PVA became prevalent. I don't have much time left, so in the next minute or so, I'd like to summarise some of our conclusions from the project. Here are the questions we asked at the start of the presentation. So for the pigments, we've shown that it is possible to use an ochre's elemental fingerprint to relate it back to its source. We saw today that samples taken from paintings can be related to ochres sourced from the same location, but it is complicated because artists from one location may use a variety of materials, even synthetic materials. So a deeper understanding of material availability and artistic choice is needed. And our success did also vary depending on the color group we were looking at. For the binders, we found that the use of binders is common and occurred before any intervention from outside the Indigenous community. Based on our study, the types of binders used is much more narrow than the literature suggests, and we found that orchid juice was widely used as both a preparatory material for the bark and as a paint binder. Our study also found evidence for the extensive, often undocumented consolidation of these paintings. This project would not have been possible without the help and support of a great many people from all different places, and we are deeply indebted to them. I would also like to thank the organisers for giving me the opportunity to share this work with you at this wonderful forum, and I thank you all for listening. And please keep an eye out for the publication, which we hope to be able to share with you all very soon. Thank you.
Good morning. My name is Eleanor Valier, and I'm a co-director at Care of Studios in Melbourne. Today, I'll be presenting on the topic of artist mixed matte paints, research taken in collaboration with Warringurri Aboriginal Arts Centre. This research is the culmination of my minor thesis research from 2015. And to begin, I would like to acknowledge the people of the Kulin Nation, where I live and work on Wurundjeri country, and also to the Miriwong and Gadjurrung people, where a significant part of this research took place. I would like to pay my respects to elders past and present, and extend this respect to the complex systems of knowledge and oral tradition, art and language that keep culture strong across this country. The research upon which this presentation is based was conducted in 2015 as a minor thesis requirement for the Masters of Cultural Materials Conservation at the Grimwade Centre at Melbourne University. The research built upon an existing relationship between the Grimwade and Warringurri Aboriginal Arts Centre, which is an art centre located in Kununurra in the East Kimberley. The Art Centre was founded in 1985 and currently supports over 100 artists working across the mediums of paint, performance, textiles and sculpture. It is the oldest continuously operated Aboriginal-run art centre in Western Australia. As part of the treatment requirement of the course, I conducted an interventive treatment to consolidate cracking, which was found in especially matte and porous areas of a painting less than 5 years old. A research focus was discussed with Grimwade and Art Centre staff, and rather than look into consolidation methods for this problem any further, we decided to look into the potential causes of the cracking. We decided to investigate the different ratios of pigment and binder found in paints mixed by the artists and Art Centre studio workers at Warringurri. The following research is based on primary source material collected during time spent at the Art Centre in 2015, followed by scientific testing of paint formulations at the Grimwade. So our research aim was to study the effect that differential pigment binder ratios have on a paint film, and also to sort of capture what sort of pigment binder ratios artists were using at this time. So the first investigation to take place was into the materials currently used by Warringurri artists. The studio workers first of all stretch and prime cotton duck canvas with an acrylic primer. Then artists painting at the Art Centre will mix up colours as needed, often at the start of a new painting, or they may also get the studio workers to mix up a colour for them, especially the older artists. And the binder used is a PVAC glue, specifically Selleys Aqua Adhere, which is mixed along with water into containers of pigment. Prior to the early 2000s, artists at Warringurri did use a wide variety of coloured ochres as pigment, which were sourced and traded from surrounding countries and groups. Around 2004, however, senior female artists began experimenting with finely ground imported pigments in 5 base colours, and they developed the extensive colour palette that characterises the paintings coming out of Warringurri today. So the pigments currently used are imported from an art supplier in Perth and come in 4 colours, black, white, red and yellow. And then the studio workers create a 5th colour, which is a darker red, made by heating the yellow pigment. And now, although the white pigment is technically titanium dioxide, these pigments are mostly ochres and they're all referred to as ochre pigment. Due to the narrow focus required for this thesis research, we decided to just focus on the white pigment, which is, as I mentioned, titanium dioxide, rather than a traditional white ochre, which might be a kaolin or huntite, especially in that region. So white was chosen as it forms a base for many of the lighter colours used, including the predominant pink colour used in the initial painting that exhibited cracking. Data collection of the ratios used by 3 artists and 1 studio worker were conducted using the participatory action research model, in which the researcher becomes a participant observer. This data collection took place over the course of a 3-week internship at Warringah, during which time myself and a fellow intern carried out other tasks around the Art Centre, as well as sitting and talking with the artists about their practice and mixing processes. These sessions were kept informal with observation and discussion around mixing techniques and colour formation. A low-tech means of capturing the artist's ratios of pigment to binder to water was devised, marking the amount of each material as they were added to the plastic containers the paint is mixed in. This method of data collection mimics the way that the artists generally mix their paints, which is going off look and feel rather than using precise measurements. As the research went along, it became apparent that what we were really looking to determine with this research was the critical pigment volume concentration for the white ochre pigment used by Warringah artists. And at what pigment volume concentration does the likelihood of cracking occur? So the pigment volume concentration, or PVC, is only one factor that can lead to cracking in a paint film. But due to the relatively young painting that was exhibiting cracking that kicked off this research project, it was the basis for this investigation. So a brief recap of the formula used to determine the PVC of a paint film is the volume of pigment divided by the volume of pigment plus the volume of binder, without any solvents or water added. So the critical pigment volume concentration, or CPVC, of a pigment changes with different binders, as various binders interact and saturate pigment particles differently. The CPVC of titanium dioxide and PVAC glue, which is a common binder for contemporary Indigenous artist mixed paints, was not known at the time of research. Therefore, the testing that followed the data collection phase attempted to draw some conclusions about where the CPVC of these materials may lie. Paint films with a high PVC, that is a PVC that is higher than the critical pigment volume concentration, appear matte and may be porous and permeable due to the presence of irregular voids in the dry paint film. A matte finish is often a desired look, especially in the white final layer of paint applied, and numerous sources have noted the susceptibility of white paint on bark paintings or ochre-based paintings to flaking and friability. This may indicate that these paint films do have PVCs in excess of the critical PVC. As noted, the CPVC of titanium dioxide and PVAC glue was not known during this research. However, studies by Hansen into matte paints proved a useful guide for research, and the pertinent information is listed on this slide. Back at the Grimwade, the marked artist cups were used to measure out the amounts of pigment, glue, and water for each paint film, and then the PVC of each paint was determined. So as you can see, the PVCs collected ranged from 57% to 79%. Following the determination of the PVCs of each paint film, samples were prepared to be aged. The sample preparation matched as closely the process and materials used by those in the Warringah studio. 2 outlier samples were also made with a PVC of 40% and one of 90%. Most importantly for the findings, one sample was painted out in a single layer, while the second sample had 2 layers of paint for each PVC. Samples were then allowed to dry before placing them in a thermal aging machine set to 90 degrees Celsius for 72 hours to approximate 10 years of aging. As the initial painting observed with cracking was half this age, 10 years was determined to be more than enough time to evaluate the paint films. The results of the aging were the most interesting in samples with 2 layers of paint. All samples were analysed using a Dynalight at 35 times magnification. Voids were seen in all samples except for the 40% control. Studies by Wang et al. Have shown that voids may begin to appear around the CPVC of a paint formulation as pigment particles reach and begin to exceed the saturation point. Cracks occurred in artist samples that had a PVC of 67% and above, predominantly in areas where the paint was slightly thicker from overlapping brushstrokes or around corners. So here are the micrographs of the aged samples with 2 layers of paint. So at 40% PVC, only agglomerates are visible. At 57% PVC, however, agglomerates and regular-sized voids are present. There was no cracking visible in either of these samples. The presence of regular voids in 57% sample may indicate that the CPVC is around 57% for titanium dioxide and PVAC glue. Once we jumped up to the 67% PVC sample, the voids become irregular in size and there are distinct cracks between them, indicating that the PVC is above the critical pigment volume concentration. At 75% PVC, differential sized voids and cracking is also seen. As we might have guessed, at 75% PVC and at 90% PVC, many voids of different sizes and cracks are seen throughout the paint films. So from these samples and this scientific testing of the PVCs and paint films that we got from our data collection, we can deduce that the critical pigment volume concentration is around the upper limit of Hansen's 30 to 60% claim. And just, to remind you that the pigment particles will react differently to each binder. So for one pigment, for a cobalt blue or something, the critical pigment volume concentration can range from 20% to 67%, depending on the different binder used. So that's acrylic ranging through oil to egg tempera, casein, etc. So at 57% PVC with these samples, there were some regular sized voids seen, while at 67% the voids became irregular and cracking began to be visible in the samples. If I was to design this experiment again, I would like to make a control sample at 50% PVC to see if voids had started to present yet, and again at 55% and 62% PVC, just to get a better picture of how the pigment and binder are interacting at this juncture of pigment volume concentrations. From the samples tested, we can ascertain that a paint film with a PVC of 67% and higher using titanium dioxide and PVAC may be in excess of the critical pigment volume concentration and therefore be more matte, porous, and likely to develop cracking. As I've noted already, however, the PVC of a paint film is not the only factor that can cause cracking. As we saw ourselves with our samples, that only the samples with 2 layers of paint actually exhibited voids and cracking, whereas the single layer, they all looked pretty good. So factors such as the application, interaction of different pigments, and vibration from travel are also contributing factors to why a painting might crack. So as with all good research, this research did bring up quite a few more questions than it may have answered, but there were some limitations to the research. So it's just a brief look into this area of matte paint film formulations as mixed by artist paints. And there's obviously a lot of variables that are very hard to capture in this sort of small scale research project. And we can't draw too many conclusive outcomes for the formulation of matte artist mixed paint films on the whole. However, I do hope it might serve as a starting point for more future research in this area. Doing similar studies into the remaining 4 base pigments used at Warringurri would be really valuable, as well as colour mixes. Although again, there's a lot of variables that could be come into play when we get into colour mixtures. Not to mention the fact that artists mixing paints may not do it exactly the same every time. That's just something that we need to accept with this sort of research. It would be interesting again to sort of repeat the data collection on the white pigment just to see how reproducible, I suppose, those ratios were. So rather than using this as like a way to point to one artist's paint mixing style as more susceptible to cracking or anything of that nature, I think it's just an interesting jumping off point to think about how matte paint films can be studied in order to figure out if the matteness of the paint and the way that it's formulated does contribute to any susceptibility to cracking that might occur later in its life. So as well as the colour mixtures, I think that would be really interesting, especially if we're looking into the pink that's mixed, for example, because obviously the titanium dioxide and the red iron oxide pigment particles have different sizes and different saturation points, and different thirstiness, for lack of a better word. Looking into sort of how they interact would be really interesting as well. So it would be really interesting, I think, to approximate the critical pigment volume of each pigment by testing the PVCs at regular intervals of 5%, starting from maybe 45% and going to 70%, for example. There's probably some other ways you can determine the critical pigment volume concentration a little easier, but just following that same low-tech data collection, I think that could be really interesting. Another limitation of the research was, of course, the outsider status of the researchers and also the short time frame of the data collection. So having the ability to build stronger relationships with the artists and have ongoing dialogue with the Arts Centre would strengthen this and any future research. The artists were really generous sharing their knowledge and their time, and so that would take me on to my thank yous. So to finish, I'd just like to say a really big thank you to all of the artists, art workers and staff and studio workers present in 2015 at Warringurri Aboriginal Arts Centre for their time, knowledge and generosity in assisting me with this research project. A big thanks also to my supervisor, Sophie Lewenkamp, my fellow intern Jasper Coleman, and also to Dr. Lyndon Ormond Parker, who was present for some of the internship as well. Thank you very much for your time.